What are real-world quantum noise models and error correction? Have you ever wondered how quantum computers manage to keep their data intact despite the many errors that can occur? Today, we will talk about real-world quantum noise models and error correction. These models are vital in understanding how errors affect quantum information during computing operations. They help in designing and implementing quantum error correction codes, which are essential for protecting quantum data from various errors. Quantum noise can take several forms. One common type is the bit flip error. This happens when a qubit, which is the basic unit of quantum information, flips from one state to another. For instance, it can change from 0 to 1 or vice versa. Another type is the phase flip error. This error alters the relative phase of a qubit state without changing its value. Next, we have amplitude damping. This type of noise models energy loss processes. For example, a qubit can lose energy and transition from an excited state to a ground state. Then there is depolarizing noise, which is a simplified model where a qubit randomly experiences any of the bit flip or phase flip errors with equal chance. Leakage errors occur when a qubit moves out of its intended computational space into higher energy states, which standard error correction codes cannot fix. In real quantum hardware, noise is often biased. This means that some types of errors happen more frequently than others. For example, certain qubit designs may experience more phase flip errors compared to bit flip errors. Understanding this bias allows for tailored quantum error correction protocols that improve performance by focusing on the most common error types. Mathematically, quantum noise models are represented using quantum channels or error operators. These help in capturing how errors transform qubit states. They guide the design of quantum error correction codes like the surface code. This code arranges qubits in a two-dimensional lattice, making it effective at detecting and correcting errors, particularly for common noise types. Real-world applications of these noise models in error correction include optimizing quantum error correction protocols. By taking into account noise bias and specific error characteristics, these codes can be adjusted to significantly lower logical error rates. Additionally, noise models aid in developing error mitigation strategies. This means creating quantum circuits and error correction codes that can handle amplitude damping and leakage errors more effectively. Understanding noise sources is also crucial for benchmark and improving hardware. By knowing where noise comes from, engineers can work on extending qubit coherence times and enhancing quantum control fidelity. This directly contributes to more reliable quantum computing. However, challenges remain. Real-world noise is complex and often not fully captured by simplified models. Accurate noise characterization demands detailed experimental data and advanced modeling techniques to reflect correlated errors and hardware-specific effects. Mastering real-world quantum noise models is essential for advancing quantum error correction. This knowledge is key to developing more reliable quantum computers, enabling them to perform longer and more complex algorithms. As we continue to improve our understanding of these noise models, we move closer to achieving practical quantum advantage.